Folks, here we are, chapter 23, and this is all about signal transduction. Now there is a chapter 22, obviously, it comes before 23, but that is about neurotransmission and neurobiology, and I'm going to leave that to physiology so that we can focus on the cell biology of primary messengers, secondary messengers, and receptors. So the first thing we're going to take a look at is chemical signals, and I've broken this down into several videos like before, so I try and keep them short. I can't promise that I can always do that. And we'll start thinking about the relationship between signals. And we're going to think about chemical signals, mainly soluble ligands, and the relationship with their receptors. So that's the first thing we're going to get doing. We'll start maths in general, and then we're going to get into some maths. So I'm going to get going quick before you freak out too much. So as you know, cells produce signals. In some cases, that is by displaying molecules on their cell surfaces, or they may release chemicals into their environment, which other cells, either close by or more distant, respond to. And then multicellular organisms benefit from this because they can regulate and they can coordinate various activities of cells and tissues using those signals. So although we're talking about this in the context of metazoans, complex animals, you do see this down through simpler animals, all the way down through the kingdoms, all the way down to bacteria use signals to communicate both between individual cells and actually in groups of cells in a process called quorum sensing. So you probably remember from general biology that signaling molecules and signaling systems can be classified based on the distance over which the signal acts. So the distance between the site of production and the site of response. So endocrine signaling, this kind of thing on the left here, is the kind of realm of endocrinology and hormonal signaling studies. There you have the signal produced in one cell, and then the response is in a target cell, which is very distant from the cell producing the signal. And so that's usually signaling through the through the bloodstream. Paracrine signals, kind of thing that's going over on the right. Those are diffusible locally, and they act over very short ranges. Kind of signaling called juxtacrine signaling, that requires direct contact. So you may have heard that as contact-dependent signaling. Autocrine signaling is like paracrine, it's very local, but there the signal acts on the same cell type that produces the signal, and that can be perturbed and interfered with in certain diseases. Cancer springs to mind because I teach that. So that's a quick overview. So when a messenger molecule or signaling molecule reaches its target, it binds to receptors on the surface of the target cell. Now, there are exceptions. There are nuclear receptors and cytoplasmic receptors, and we're going to start off just thinking about receptors on the cell surface and keep it simple that way to start with. So the messenger, the chemical messenger, is called a ligand, and that's from some Greek or Latin meaning to communicate or to send or to bind, I think. So we have ligand production, and we could go back and think about how that ligand is produced and secreted. We have reception on the cell surface, and we have the ligand binding into a small pocket made of amino acids on the receptor on the cell surface. That's the first step in cell-cell signaling, reception of the information. Now that can lead to the production of secondary signaling molecules and then tertiary signaling molecules. It could lead to an increase in certain ions inside the cell. So for example, the opening of calcium channels in the endoplasmic reticulum. And then this whole transduction pathway then elicits some kind of response in the cell. And we can think about responses in terms of rearranging the cytoskeleton, activating enzymes for glycolysis, or we could think about anything which is dependent on a change in gene expression. So let's think about the nature of these ligand-receptor interactions. I apologize, my air conditioning has come on. I'll try and speak a little louder. Now, this is going to be kind of familiar to you because if you think back to our discussion on interactions between enzymes and substrates, much of this will be the same. So the binding of a ligand to a receptor is very much like the binding of an enzyme and a substrate. So when a receptor is bound to a ligand, it's said to be occupied. and as ligand concentration increases locally, then we get closer and closer and closer to the point of saturation, and that's when all of the receptors will be bound. So obviously you can't have saturation unless you have a greater concentration of ligand than receptor, and that's not a difficult situation to actually reach. So there's this relationship between the ligand concentration in solution and the number of receptors occupied, and we can describe that relationship in terms of the affinity of the ligand for the receptor. So the dissociation constant here, Kd, that's the concentration of free ligand. That's what the square brackets around the arrow means. Square brackets means concentration. That's the concentration of free ligand when 50% of the receptors are occupied. Okay, I say it again. Dissociation constant is the ligand concentration when 50% of the receptors are occupied. So, what this means is that if you have a low Kd, you have a high affinity, and vice versa. Low affinity is a high Kd. So actually think about what this means. If you have a ligand which has a very high affinity for the receptor, that means it's going to bind very quickly and very easily and stay there very tightly bound. You don't need much of that kind of ligand to saturate 50% of the receptors, because as soon as you've got the ligand present, it's going to glom onto the receptors. The other hand, if you've got a chemical with a low affinity for its receptor, then you're going to need a high concentration, a high Kd. You're going to have a high concentration to get 50% of the receptors bound, because it's going to be kind of like, I don't really want to bind it, I'm going to bind and let go. And so think about what this Kd actually means. It's the ligand concentration when 50% of the receptors are occupied. Now, you can memorize that. That's a description. But I want you to be thinking about explaining it based on affinities. Okay? High affinity, low Kd. Why would that be? So keep thinking about that. Okay, so let's think about a situation where we've got a hormone, H. So the concentration of the hormone, that's the ligand, is in square brackets. And a receptor, concentration of the receptor, as a cell surface receptor or a intracellular receptor, a concentration of R in brackets. When those two interact at equilibrium, we get there's this obviously an equilibrium between the hormone concentration and free receptor, the hormone and free receptor, and hormone bound to the receptor. So this here just describes a situation where there's a hormone and a receptor, and we're allowing the system to come to equilibrium. So it's certain that we're going to have a certain amount of free hormone based on its affinity constant, a certain amount of receptor, and then a certain amount of hormone-receptor complex. And hormone and receptor are associating in dissociation. This is not the case where all of a sudden receptor is bound to ligand and you can never reverse it. Okay, this means that this is a reversible process, and we're describing the situation here at equilibrium. So we talked about dissociation constant. It's often easier to think about the dissociation constant in terms of the association constant, also known as the affinity constant. And so that is simply the concentration of hormone, ligand, bound to receptor, divided by the concentration of free hormone, free ligand, multiplied by the concentration of free receptor. So that's the association constant. And then the dissociation constant, which we mentioned just now, is the reciprocal of that. So we just flip the bottom of the equation on the top, and the top on the bottom. We make a reciprocal. And so that's the dissociation constant there. So it's just the inverse of this. So if you remember this, you've got this. And if you remember this, you've got the affinity constant. So sometimes it's a little easier to think about these relationships in terms of what we call fractional occupancy. So the fractional occupancy is the fraction of receptor bound by ligand. That's pretty straightforward. It's the ratio of ligand bound to total concentration of receptor. So ligand bound here, that's hormone associated with receptor, that's bound ligand. And then we've got free receptor and then ligand bound receptor. So both of those together make up the total pool of receptors. Think about the receptors. They can either be ligand bound, that's this population, or they can be ligand free, that's that population. Okay, so the total concentration of ligand bound divided by the total concentration of receptor gives us the fractional occupancy. Okay, it's just a ratio basically. And you can do some algebra and some rearrangements of substitution. You come up with this equation here. Don't worry about that too much. But what it is useful to think about is what these equations mean. So when the ligand concentration is 0, okay, the fractional occupancy must be 0. You cannot have any receptors occupied when you don't have ligand. So what is the other extreme of that? When the ligand concentration is many, many, many times the dissociation constant, remember that's the concentration of the ligand to get 50% receptors bound, then the fractional occupancy approaches 1. So you've got two extremes here and then everything in between. Okay, ligand concentration is 0 and basically then saturation. Okay, and then we've got to describe what happens in between there. And so the in-betweeny part really is the KD. We can rearrange, we can do some thinking about this equation here and say, okay, what would the fractional occupancy be when 50% of the receptors are bound? And all we're basically doing there is thinking about what this means in terms of the dissociation constant. And we can rearrange this all down here to this at the bottom, and I don't want you to worry about this. You've actually seen this before. This is called the Scatchard equation, and you've seen that before in some of your homework problems or data analysis. I don't call Rich 1. So don't worry too much about this down here. I just wanted to show you it because I know you've seen Scatchard plots before. But what we end up with is this relationship between where we get 100% of the receptors bound when basically the ligand concentration is many, many, many times the dissociation constant. And you've seen that before. You've seen the situation where you have a substrate concentration which is many, many, many times the Km. And so KD here is very much like the Km, and the Km is half Vmax. So the KD here is this concentration here, looks like about 5 nanomolar, where we have 50% of the receptors bound. So KD is kind of like Km. And then up here, Vmax, in terms of substrates being converted to products, if you think about enzymes, that's what this is like up here, where ligand concentration is many, many, many times the KD. And then down here, we've obviously got the situation where the fractional occupancy will be 0 because there's no ligand present. You can't have any receptors bound if there's no ligand present. So think about the actual KD and what that means in terms of the affinity and dissociation constant in terms of the receptor-ligand interactions. Okay, we'll stop it there, and I'll come back with more information about chemical signals and receptors next time. I'll see you soon. Bye for now.